Yeah, I'll take questions later too. All right, so one of the ways we can use the energy from a nuclear decay process or nuclear reaction is a nuclear power station like this. Did I talk about this already? Okay. This is relatively safe and clean energy, except you have a problem with waste. You know, the waste isn't clean. The waste is going to be contaminated with radioactive daughter products, right? And this isn't necessarily safe. Because what happens if the cooling system malfunctions? If the cooling system malfunctions, like at Fukushima, then the core is going to melt. It's going to get too hot. You know, the core just is uranium. Uranium is a metal, a heavy metal. The melting point isn't so high, and so it's not so difficult to melt this stuff. But we looked at this slide already? Yes. Yeah. So nuclear would be a good option if they can make sure that cooling system is functioning. So we'll look at this.
Hi, I'm Arnie Gunderson from Fairwinds Associates. It's Sunday, April 10th, and for a change of routine, I wanted to do a science experiment today. Back in 1978, I was the lead nuclear engineer on a project in upstate New York, and the company I worked for at that time bought the last nuclear reactor that was ever bought during the first nuclear renaissance. The project was later canceled, but as part of that, one of the things that the vendor gave to me we bought the reactor from was a piece of a nuclear fuel rod. This is a nuclear fuel rod. This is zircaloy. And it's the element that's inside of the Fukushima reactors. Now these are about 12 feet tall, and there's thousands of them inside the Fukushima reactor. This is a simulated pellet of uranium. Now it's not the real thing, it's plastic. If it were the real thing and had been operating in Fukushima, I'd be dead by now. But these pellets go into these fuel rods, and over 4 years create a lot of heat. When the reactor shuts down, they remain hot. So what I wanted to do today is to show you what happens to zircaloy when it gets hot, as it happened when the water stopped in the Fukushima reactors. Okay, we've got our experiment set up here, and this is what we plan to achieve. Here's that fuel that I took the plastic out, and we're going to heat it with a torch to simulate the heat that's coming out of the inside. Then we're going to spray water on the outside, and you'll see steam coming off, which represents the steam that's coming out of Fukushima right now. Now, in that steam is also hydrogen gas, because the water hits the zircaloy and creates not just steam, but hydrogen gas. This is my friend Jim. He's a great neighbor, and he's going to be the acetylene torch person.
Water can oxidize the metal here.
Okay, the zircaloy is sugared in, and now I'm going to spray it with water as if it were getting some water in the bottom of the reactor. we just did was we oxidized the zirconium. You can see it's a different color now. The metal that was quite strong becomes very, very brittle. And we were just able to break pieces right off the end of it. Well, inside the nuclear reactor, it ran at that temperature for 7 to 12 hours. The fuel got brittle, and all those nuclear pellets then were allowed to fall out. We just created what went on inside the Fukushima reactor. Those rods glowed that hot for 12 hours or more. Now what happens is we've created an oxide. This is zirc oxide now, and it's very, very brittle. I think you can see these sharp edges. So the fuel that was inside is now free to fall out and onto the bed of the nuclear reactor and begin to melt through, as is happening right now in Unit 2 at least, and perhaps Unit 3 as well. Well, thank you for watching. Arnie Gunderson Fairwinds, and we'll do another video in a couple days. Thank you very much.
I'm Arnie Gunderson from Fairwinds. Little change of venue today. There's been some reports in the press about a hydrogen buildup inside the containment at Fukushima, and along with that hydrogen gas, there's a discussion that there's some radioactive isotopes that are in the containment that could only be caused by a fission. Well, I thought I'd simulate today what a hydrogen buildup inside a containment looks like. Now, we're going to use this bottle as a containment, and I'm going to generate hydrogen gas in this little flask. Those nails are coated with zinc, and I'll add some acid to the zinc, and we'll create hydrogen gas out this hose. Put the hose in the bottom of the bottle, and hydrogen, being lighter than air, is going to push all of the gas out of this bottle. We'll be left with a bottle full of hydrogen. All right, let's see what happens. This is something you shouldn't try at home. I'm wearing gloves, and we've got a fire extinguisher in the corner, as well as bountiful water, just in case. Again, don't try this at home. All right, here's our beaker. And this is muriatic acid. And those bubbles are hydrogen gas bubbles. That are filling this containment, this bottle, with hydrogen. Now we're going to wait a little while here for this bottle to completely full. Again, hydrogen's lighter than air, so it's going to float to the top. And then it's going to gradually push all of the air out of this container. Now we've waited about 4 or 5 minutes, and this bottle should be filled with hydrogen gas. All those bubbles ran out that hose and filled this bottle with hydrogen gas. All right, I'm going to take the hose out and set the acid aside, because the next part of this lab is inside the bottle. All right, now hydrogen gas is lighter than air. So we put it in the bottom, but there's no place for it to go at the top, so it's going to stay in there. It's not going to leak out. Well, now I've put a little hole in the top of this bottle, and I'm going to light it with a match. Now what's going to happen is you're going to be seeing a little tiny flame up here, and that's the hydrogen gas escaping. It's barely visible, and I'll try to enhance it in a minute. Now there's a little flame at the top of this. It's made of hydrogen gas, pure hydrogen gas. You can see I just lit this. Notice the bottle is not burning. It's just the very tippy top of this. That's hydrogen mixing with the oxygen and air, forming that flame at the very top of this bottle.
I don't believe anything
No.
the government tells me.
Yeah, actually this,
I consider them to be symbols, and I need symbols to the symbol-minded.
this was not off his website. I should have gotten it off his website. This is a YouTube video. So somebody edited it. But that noise is the hydrogen there.
Ladies and gentlemen, it's time for joy.
What time is it?
What time is it?
Is that
Well,
from there?
do people bother you with that?
The situation is not stable at all.
Bothers me, man.
What time is it?
As though I personally am responsible for keeping time.
Well, that's a hydrogen deflagration.
Nobody knows what time it is. What time is it? All the calendars are different. Chinese, Hebrew, Western. Nobody knows when it is. Might be last week for all we know.
That's the smaller of the two shockwaves. That's what happened inside unit 1. When you get oxygen, what happened?
Where's his doctor?
That's the smaller of the
Right,
two
where are his
shockwaves.
goggles?
That's what happened inside unit 1. When you get oxygen coming in and hydrogen in just the right color of hydrogen.
All right, here. Okay, here's the noise. No, that's real noise. That's real. It's just burning out. Then a
The situation is
flashback.
not stable at all.
He didn't put that in there. Somebody edited his video.
Well, that's a hydrogen deflagration. That's the smaller of the two shockwaves. That's what happened inside unit 1. When you get oxygen coming in and hydrogen in just the right amount, 2 to 1, they combine to form water vapor, and they create a lot of heat and an explosion. Now, what's TEPCO doing to avoid this? The containment is leaking. We know the containment is leaking. Well, instead of allowing oxygen to leak in, they're keeping adding nitrogen inside this vessel. So that hydrogen's at the top, but they're not allowing the oxygen to get in because they continually add nitrogen to the vessel. Nitrogen is inert. So as long as the inert nitrogen and the hydrogen exist inside the containment vessel, then everything's going to be fine. The gases from our experiment were generated chemically, but of course, in the nuclear reactors, the chain reaction and the radioactive decay creates hydrogen gas. So that part of the lab is different, but the containment is just the same. It's just that TEPCO's containment is a couple million times bigger than my soda bottle. As a reminder, this November we're asking for your financial support
All right.
so we can
He
get
has his own little educational institute donation. Just one more video.
Good evening. I'm Arnie Gunderson from Fairwinds. We've been getting a lot of emails at Fairwinds on many topics, but one topic's generated an awful lot of questions and concerns and some really thoughtful remarks. And that's what happened in Unit 3. Why did that explode the way it did compared to Unit 1 and all the other reactors on site? So today I want to use the opportunity to talk about what we know for sure about Unit 3 and a couple theories about what could have caused the devastation we see at Unit 3. Well, to begin with,
the Unit 3 explosion is much more dramatic than the Unit 1 explosion. Now, engineers have a term called detonation, and they have a separate term called deflagration. What that means is they're both explosions in lay terms, but a deflagration is when the wave, the shock wave, travels at the speed of sound. A detonation is when the shock wave travels faster than the speed of sound. And a detonation is much more damaging than a deflagration. So that may seem like a technical nuance, but it's really the difference between what happened on Unit 1 and what happened on Unit 3. If you look at the plume that was generated at Unit 1, it kind of moves away from the building at a much more leisurely pace than what happened at Unit 3. And I'd like to go into a couple things we know for sure about Unit 3, and then postulate the reason why I believe it happened. Well, first off, it's obviously a much more massive explosion than Unit 1. The second thing is that there's a large amount of energy that goes straight up. Now we would call that a vector. There's an upward vector on Unit 3 that Unit 1 doesn't have. And that's an important clue there we'll get to in a minute. The next thing is that it's clear in Unit 3 that there's an explosion. If you look at the south side of the building, that's the right side of the building, there's a bright yellow flash before the black smoke begins to go upward. That's another important clue we'll get to in a minute. Well, the other thing is that fuel rods were discovered, pieces of nuclear fuel rods were discovered as far away as 2 miles from the plant. Now, if you look at Unit 4, which we've talked about in the past, the fuel rods are dry, but the fuel racks are intact. So it's really unlikely that nuclear fuel rods could be thrown from the Unit 4 pool a couple miles away, which leads us to the fact that the fuel that's been found off-site had to come from Unit 3. Well, the other things that have been discovered is that uranium as a very fine dust has been found in Hawaii and on the West Coast. Plutonium has been found on the site as a very fine powdery dust. And another element called americium has been found in New England. Well, all of those are what we call transuranics. They're heavier than uranium. And that's an indication of that nuclear fuel was damaged and that nuclear fuel was volatilized at Fukushima. The other things are that the photographs of Unit 3 after the explosion indicate that a large portion of the building is missing, especially on the south side. But yet the infrared picture of the same building shows a heat source still on the south side. Well, last but not least, as it were, sure, the data indicates that the containment itself and the reactor itself on Unit 3 remain intact. So we've got a mystery here. We've got a reactor and a containment intact, but we know the building is blown to smithereens. Why? I believe that the fuel pool, which is a large 50 by 50 by 50 feet deep container, was empty. And it filled with gases and blew upward. Now the top of that pool would be open, the sides would be a barrier, and that could be the cause of that upward projection of material. Now that accounts for a couple more things. But basically what I'm saying is that the fuel pool is like the muzzle of a gun. It was pointing upward and it blew upward. And the other thing is, if you look at the photos, there's an awful lot of rubble coming back down. Now that's fuel racks, fuel rods, and pieces of uranium and plutonium. So that accounts for the fact that uranium and plutonium were found as far away as a couple miles off-site. The other thing it shows is that the blackness of that cloud indicates that uranium and plutonium were volatilized. In other words, they were turned into a really fine aerosol, which can find its way across the Pacific and in Hawaii and on the West Coast and now here in New England as well. So here's the question. What caused that upward force? Well, if it were just hydrogen, a hydrogen-oxygen reaction would create water. And when that happens, the sound wave travels at the speed of sound, and it's a deflagration. That's what happened in Unit 1. It's dramatic, but it's not explosive. What caused the explosion in Unit 3? Clearly there was an explosion for two reasons. One is the magnitude of the plume moving upward, and the other reason is the red flash on the side of the building. A deflagration doesn't give a red flash like that. A detonation does. So the question is, what caused the detonation? A hydrogen-oxygen reaction alone won't do it. There has to be something more here. And the jury is still out on why. But a plausible reason is that a hydrogen reaction started, which then caused a shock wave to move and distort the nuclear fuel in the pool. The distortion of the nuclear fuel in the pool creates a prompt nuclear reaction, which then blows the rubble out of the pool up in the plume and creates the energy needed to create the dramatic event that we've seen at Fukushima Unit 3. There is a way to test this hypothesis, and the way to test it is to look at the types of isotopes that are in that smoke. Now, we know the military had planes up, and we can also assume that there were laboratories counting the material. And there's two xenon isotopes, and depending on their ratio, we can determine if it was a prompt criticality or not in that fuel pool. So the evidence is there, but we're not getting it yet. But I would assume that our government has it. Well, thank you very much, and as more information becomes available, I'll keep you informed.
So what he was saying is that that other explosion was a small nuclear explosion, you know, and from the shock wave of the hydrogen explosion distorted the fuel to cause it, a prompt nuclear reaction rather than a full-on nuclear explosion, but a small one. And there have been those in the past, actually. All right. And so as long as that doesn't happen, you know, nuclear reactors are very attractive because of the well, I don't know. They're very attractive because they don't produce greenhouse gases, so that's one. But other than that, they can produce byproducts or daughter products which aren't so great. In fact, one of them would be plutonium. So this is from a breeder reactor. A breeder reactor is actually producing, usually this is just waste products, but in this case, a breeder reactor with U-238 can actually produce plutonium-239, and the plutonium can be used as a fuel or as a bomb material. And so in this case, this forms plutonium, and so as a breeder, it breeds new fuel here, the plutonium. However, plutonium is very toxic. Did I tell you the lethal dose of plutonium the other day? Well, the lethal dose, I think the LD50 for plutonium is 1 microgram. You know, it doesn't kill you right away. You know, it just causes cancer or something and you eventually die. But a microgram, how much is a microgram? And so a dollar bill is said to weigh 1 gram. And so if you take a $1 bill and chop it up into 1 million pieces, and then take one of those pieces, that's a microgram. And so it's barely anything, right? That's it. Well, there's lots of plutonium there in Fukushima. Plutonium is highly poisonous and has a long half-life. The half-life of plutonium is 24,000 years. So if you use the, the 5 half-life guideline, then, that's like 125,000 years before that. All right, an alternative to fission, which produces a lot of radioactive byproducts, is nuclear fusion. Fusion is what produces the energy of our sun. And there, you take, for example, 2 hydrogen atoms to form a helium. Well, helium will have a stronger nuclear binding energy per nucleon. And therefore, what we should see is this. This should be exothermic here. And we can actually calculate how much energy is released here by summing up the mass of the products minus the mass of the reactants to get our delta mass, and then calculating the energy associated with it. And the energy is huge, like uranium. We're talking enormous amounts of energy. Well, we don't form radioactive products here, we just form helium. Helium's inert gas, and this is not helium-2+. In other words, alpha particles. These are helium atoms here. But one thing that isn't good are neutrons. Are neutrons good for you? No, neutrons are very bad because neutrons meet no resistance in reacting with the nucleus of non-radioactive atoms, right? And so if you were to bombard yourself with a lot of neutrons, all the carbon in your body, a lot of it can be converted into from carbon-12 to carbon-14. Well, carbon-14 is radioactive. Nitrogen can become radioactive. In fact, anything exposed to neutrons is troublesome, but you can get rid of the neutrons. Well, this is very promising because you can get rid of the neutrons or use them, and we have a good source of energy without the radioactive daughter products. But the problem with this is you need plasma temperatures, and you need temperatures over 40 million Kelvin to get this reaction to go. The reason you need such high temperatures is that, these things don't want to come together to react. The 2 nuclei want to repel each other. And so you have to overcome that by either high temperatures or you use an accelerator. And if you use a linear accelerator or a cyclotron, then you have too little reaction to generate much energy. And so what they're trying to do is they're trying to generate larger amounts of energy by using larger quantities of starting material there. Well, 40 million Kelvin, what's the melting point of most containers? Maybe all containers. All containers at 40 million Kelvin, you're going to melt it or vaporize it, right? And so that's a problem. These other details, I'm not worried about. But it does have the advantage. Hydrogen is one of the, or not one of, hydrogen is the most abundant element in the universe. There's plenty of hydrogen around. You can also get it from water. Here's a fusion reactor, and if 40 million Kelvin gas were to come into contact with metal here, it'd vaporize it. And so that gas cannot come into contact with any of the surfaces here. And so what it is it's magnetically confined or electrically confined to the region between here. And so this is using magnetic confinement. And so it's just stuck in space. It doesn't have to touch anything. And that would be it. And so there are a lot of technical challenges to get. And so far, I think the latest I read was they were getting a little bit of energy from this, so, but not a lot. You need a lot of energy to keep this self-sustaining. And so it's back to fission reactors. That was a fusion reactor. Fission reactors are going to generate all those radioactive daughter products. And so let's take a look at the effect of radiation on matter, ionizing radiation. Ionizing radiation would be alpha, beta, gamma rays. If we look at the power of the ionizing radiation, we see that alpha is at the top. Now, alpha are incredibly powerful oxidizers, so they're going to react. And then beta and then gamma. But you don't have to know that order. You should just know alpha is very dangerous. So we could have ionization processes. You know, here's an alpha particle. If it hits an atom, it can knock an electron off, or it could strip electrons, depending on how fast this is going. This electron that's ejected, boom, hits there and can maybe knock off secondary electrons. That's not so important. How do we measure radiation? We could use a Geiger counter. Geiger counter, there's a low pressure gas in here, and the gas doesn't conduct electricity. However, if ionizing radiation comes in and strikes the gas, then it forms ions, and the ions will conduct electricity. And so over here we have high voltage. You know, here's positive electrode, here's a negative electrode. So we're trying to pull electrons in here and then push electrons out here. But nothing's going to close this gap because it's too much of a gap to jump. Unless there are ions. If there are ions around, then we'll get an electric current set up and a signal on the Geiger counter. And so this is what a Geiger counter looks like here, like this. And on the end there's a mica window, so we could just listen. You hear the little clicks? This is a signal from when ionizing radiation comes in, creates ions, and then there's electric current, and each time we get that, you hear that little beat. Where's the ionizing radiation coming from? Well, this is normal background radiation. Normal background radiation comes from cosmic rays, or continually passing through Earth. Cosmic rays are high energy. So we're exposed. The higher the elevation you go, the more cosmic ray will be a factor. And so in Denver, the background radiation is much higher than the background radiation at sea level. If you take this on an airplane, then it would go crazy. I took a Geiger counter on an airplane once, just to see. And I had to turn it off because, no, but I did. I mean, this was a while back because it's, no, nothing. So I was just listening to it, and then, it was going crazy, and I had the thing on, and so I had to turn it off quickly because it was attracting too much attention. But all right, so here's some uranium ore. This is just rocks mined out of Arizona and Nevada. I think these samples were picked up in Arizona, just really pretty rocks. Right? But, listen to this. Yeah, and so there's uranium in here. And so we got some samples. These are just purchased, I think, in Arizona. There's uranium mines you can take tours of and stuff. And you can buy, if you want to buy a sample, you can buy a sample of uranium ore. But, even though this was pretty active, did you hear all this? When I took it on the plane, it was much more than this. Well, there's some lead. Do you see the lead foil to protect your cells? I'll just leave it over here. The janitor. Let's see if I got any uranium on my fingers. I'm okay. Uranium is a heavy metal. And so as far as like, then plutonium, you know, I was watching this video on plutonium, and this, this was when they're just for doing initial investigations of plutonium. This guy had a chunk of plutonium like this big piece of plutonium, and was cutting it with a knife, saying, "Oh, look how soft the plutonium is." You know, but you know, I think years later he wasn't around anymore because the lethal dose is pretty high. What's that? Cell phones give off radiation? What kind of radiation? Cell phones do. They give off, but not ionizing radiation. But you know, there's still talk. Like for example, they say you shouldn't hold it here because it creates magnetic fields, and magnetic fields can disrupt cellular processes. And so I think there's a study where they say there's more tumors from people holding the, benign tumors maybe from people holding the phone against their ear. So they say always use speakerphone. Have you heard that? Because of the magnetic field.
You know how like you wear the Bluetooth thing?
Yeah.
They said some lady got cancer and it was in the area where she was wearing that.
Oh, really?
Yeah.
Oh, that's too bad.
But it's obvious because she was wearing it a lot. She was avoiding.
Well, I used to work with powerful magnets in nuclear magnetic resonance, or MRI type magnets. And so I went to a conference in Monterey, and one of the hot T-shirts there was that there's no adverse effects of magnetic fields, and then they had a whole bunch of conehead people on the shirt, and everybody thought it was a big joke because magnetic fields, it's not going to do anything, at the time. And so there are lots of people who say that's that might not be, but. Anyway, so we could detect this. This is what the biochem lab. This is what the biochem lab looked like next door to my lab. They're always looking for like this. This is the schools. You can buy one of these. It depends. If you get one that's calibrated, these things have to be calibrated. It's supposed to be calibrated once a year. If you buy one that's calibrated, I forgot how much. It's like $200 or something for this style, used. But you can buy a little personal one. The one I took on the plane wasn't this. It was a little one, personal one, dosimeter. No, nobody approached me, but it was starting to make so much noise, so I turned it off. Yeah, and it was very loud. And the alarm, the little personal one had a little alarm because it was set. Like if it goes above this amount of radiation, this hazardous. And so alarms started going off. Wee, 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 something like that. And then it was clicking wildly. That's better than when I used to work with X-rays or X-radiation, we used to have a radiation badge. And at the end of the month, we would turn in our radiation badge. And then, they'd get it developed. This is a piece of photographic film inside a dark plastic case. They develop it and look, how much radiation were you exposed to by how many spots were on the film. And so the problem is like they'll say, okay, you've been exposed to too much radiation this month. So next month, don't expose yourself to radiation because you have to keep your total exposure, annual exposure, below a certain limit. Then you go, but you don't know, like you could be standing there in front of lots of radiation and have no idea, but the badge picks it up, but it's too late by that time. And so, life expectancy well, it depends on how much radiation you've been exposed to. And in fact, they have charts. Like if you've been exposed to this many, it's called sieverts of radiation or millisieverts of radiation, then you're expected to live this long, based on the averages. And so like people who've been exposed to, acute amounts of radiation, they'll only live an hour to days, that kind of thing. But lower levels, like the person who had the polonium person, I mean, if you took the Geiger counter and probably to that polonium sample, it wouldn't have sounded so bad, right? But the problem is the person, when we're talking about radiation, and this is one of the situations that happened at Fukushima. At Fukushima, they're saying, the amount of radiation those people are exposed to is probably like, flying in an airplane. Flying in an airplane. So I thought, okay, I'll fly in an airplane and see how much radiation that is. But the thing is, once you're off the airplane, then, the exposure is gone. At least the source of the exposure is gone because you need to be at high altitude for that. And so you're back at low altitude. But a lot of the people there had ingested, the radiation, and when you ingest it, even if it's low level, it's going to cause damage. So, for example, iodine would get concentrated in your thyroid, and strontium would get concentrated in your bone. But the thing is, you can't like wash it off. If you got radioactive particles on your skin or your clothes, you can always wash it off. But if you ingest it, you can't wash it off. And so if that person, the person who ingested the polonium-laced tea, the Russian spy, he couldn't, even though I think they tried chelation. From what I heard, they tried chelation therapy, but they couldn't get the polonium out, Whereas all the other people who were exposed, yeah, they got exposed, but they washed it off, or the plates were exposed because and the cups were exposed, but they said the normal dishwashing procedure would wash off that, and you wouldn't have to worry about it for the other people who use the exact same plates and exact same dishes. But unfortunately, that person ingested it, and its biological half-life is kind of long, and it stays in the body. Although polonium's half-life isn't so long overall, it's long enough to cause some serious damage. No. Chelation doesn't work for iodine because once the iodine's in your thyroid, it stays there. And so it's not like what people do for iodine is if they get exposed to radioactive iodine, the radioactive iodine goes in your thyroid, and they'll take like iodine tablets. They'll take iodine tablets and hope for some chemical exchange. That is, some of the iodine non-radioactive will substitute for some of the radioactive iodine. In Chernobyl, there are certain regions around the Chernobyl nuclear power plant, and some of the countries gave their children iodine tablets, whereas other countries didn't give their children iodine tablets. And then they published the results of that. And the children who were given iodine tablets after the Chernobyl accident had a much lower rate of thyroid cancer than the kids who weren't given the iodine tablets. And so that's more of a preventive thing, because the children who are given the iodine tablets would saturate their thyroid with non-radioactive iodine, making it more difficult for radioactive iodine to get lodged there. If it doesn't get lodged there, then your biological system can flush it out, because the biological half-life will go way down. But if the iodine gets stuck in your thyroid, then it's kind of stuck there for a long time. And so, you could live without your thyroid. For example, they could remove your thyroid, but if they remove your thyroid, then you're going to be on hormones for the rest of your life, basically. And so, the survival rate's very high, except at what cost, So it's sad, so in certain areas they stockpile iodine, because we have San Onofre, but San Onofre has already been decommissioned. But if there's an accident there, then you want enough iodine to go around. And apparently there was some kind of study recently that there wasn't enough iodine to go around. So maybe that's why it wasn't distributed. But anyway, going back to this, let's talk about radiation dosage. You know, what is the dosage? There are different units that we use for radiation dosage. One is the rad. The rad is, you know, how many joules per kilogram of radiation. You know, one rad is 1 millijoule of radiation per kilogram. Well, what would you rather be hit with? 1 millijoule of gamma radiation or 1 millijoule of blue light, you know? 1 millijoule of blue light because, you know, a joule, like 10 joules of gamma radiation versus 10 joules of red light, they both have the same energy, but do they pack the same punch? No, gamma radiation is going to pack much more severe punch. And so rad is deceptive because, you know, it's just joules. It doesn't tell you how much of a punch those joules take. That is, are those joules spread out or are those joules concentrated? And that being the case, there's another unit here, the rem. The rem takes the rad, you know, how much energy per kilogram, how much energy of radiation, and then multiplies it by Q, you know, a biological effectiveness or quality factor. And so let's take a look at the quality of the radiation here. All right, this slide shows a little bit more. But the Q factor here, if you go down to the bottom row, the Q factor is 1 for X-rays, gamma rays, and beta particles. And so rad and a rem are the same thing. But for slow neutrons, the Q factor is 3. You know, neutrons can cause a lot more damage. And so it's 3 times. And so even though it's the same energy, it packs 3 times more punch, right? Protons and fast neutrons. Fast neutrons are going to be more dangerous and going to pack more of a punch. So 10 times the punch for the same amount of energy. But look at this. The Q factor for alpha particles is 20 times the punch. So 10 joules of alpha particles versus 10 joules of X-ray. You know, well, the alpha particles are going to pack 200 times the punch of X-ray. And so we want to know the rem. The rem are given in units of sievert. And so if we're going to have radiation exposure, we want to know, you know, what quality was the radiation. A radiation badge doesn't measure that. You know what? A radiation badge only measures something called Curie. You know, because the Curie is how many disintegrations per second, you know, how many clicks per second kind of thing. Actually, this doesn't do individual because this each click you hear is 100 disintegrations. But anyway, getting back to this, 1 Curie, which is in becquerels, is 3.7 or 37 billion disintegrations per second. 37, we don't know because that disintegration can lead to a high energy gamma ray or a lower energy gamma ray or an alpha particle or whatever else. And so what we want to know is how many joules and then what the rem is. And so the most informative is the rem in sieverts and then the rad, and the least informative would be the Curie. And so you really want the rem. This is the radiation adjusted dosage. Well, there are applications, you know. Applications would be radiation therapy for cancer. You know, radiation kills cells, and so if you could direct the radiation to cancerous cells, you can kill them. The problem is it's hard to focus the radiation just to cancerous cells, so a lot of healthy cells get damaged in the process, right? But this is something that people are looking at, using focused ray of gamma radiation, you know, to kill the cancer tumors. And other applications, the biochemists love radiation. Why do they love radiation? The biochemists love radiation because they can follow atoms through whatever, cellular respiration, you know, metabolism. And so what they do is they label, what we call label, some atoms with radioactive atoms. And they replace it, or they synthesize a molecule with a radioactive atom stuck in there. And then they watch it go through, you know, one of the cellular cycles, and then they can figure out what's going on mechanistically. And so that's why they're always following things, the Geiger counter, etc. There are lots of applications of radiation, of radioactive particles. And so this is just for general interest. So I'll stop here, we'll take a break, and then I'll say a couple more things, and then we'll go to review mode.